Welcome back, Regents students, to our sixth lesson in the waves topic, standing waves. You should have already seen the video that I included in this assignment, a YouTube video that shows a standing wave. Again, if we were in the classroom, I would just grab a wave from the storeroom and start shaking it and show you what you saw in the video. But because of the closing, you have to watch the video instead. And what you should have seen is that when the person shook the spring, they could create a wave that it's an illusion that it's not moving in the spring in the forward or backward direction, that the wave is standing in place. It's not moving side to side. The vibrations are just going up and down in a spring line like this. Again, that's an illusion, something that they didn't explain in the video because the video only showed the standing wave. Standing waves are created by two techniques. What's really happening is you're sending waves from opposite directions towards each other. So one technique is you have two people on either end of a spring and they're shaking the spring and sending waves toward each other. A and B make identical waves. That means the same wavelength, same frequency, and same amplitude. These waves come to each other. When they meet, they create moments where crest overlaps crest, or constructive interference. Later, when the waves continue to move, this crest will meet this trough, and that will be a crest and a trough, and it'll make a moment where the spring is not moving. And then later, the trough will meet a trough, and then it'll create a big giant trough. So there'll be crests, zero, troughs that go like this, two waves moving, but yet it looks like there's no wave moving side to side. It's a standing wave that's just oscillating this way up and down. The second technique, like the way they created in the video, they didn't have two people. They had a person, one person, sending one wave toward a fixed point. And the reason why you don't need a second person here, remember from way back when we first learned about waves, waves reflect. And so when this wave hits here, it reflects. So you keep sending waves that eventually reflect off the wall. And that's how you get the two waves meeting each other and interfering, constructive, destructive, making crests and troughs oscillating. Okay? As you also saw from the video, you could shake at different rates and make different number of segments of standing waves. If you shake slowly, like they did at the beginning of the video, you create just one segment. If you were to snap a picture at this instant, you would see a crest. But if I snapped a picture later, I would see a trough. So we have crest, trough, alternating in the wave, filling the whole wave, filling the whole spring. As they labeled in the video, the places of the spring that are never moving are called nodes. So the ends, this is tied to a wall. This is just the person sort of giving a little bit of a shake, but essentially it's hardly moving. We call that a node, points of no motion. The place that has the maximum motion, AN is what I labeled it, but it's actually called an antinode, points of maximum motion right in the middle. Maybe right next to it moves 0.9 meters, and then right here moves 1 meter, and then a little bit further moves 0.9. So that place that goes 1 meter is like the maximum motion for a particular part of the spring. That's what we call the antinode. Okay, and of course there's a certain length to the spring. Now, if we wanted to find the wavelength of this standing wave, we snap a picture. We notice this is not the wavelength, because a wave has both a crest and a trough. So if we were to sketch a trough in there, imagine a trough over here, we would see that the wavelength is actually twice the length of the spring. We need this and then another same segment to create a whole full wave. In other words, the wavelength is 2L. Like if the spring length is 4 meters, then the wavelength is 8 meters. Okay? And so what you could do is you could calculate the frequency of oscillation. If you knew the speed of the wave in this particular spring, that it moves side to side, That's, by the way, fixed. It depends on the spring coil. Like when we learned in sound, the speed of the sound wave depended on the temperature of the air and the pressure, 331 at STP. It had nothing to do with the frequency or wavelength of the wave. It only depended on the air that it was moving in. Same thing here. The speed of the wave has nothing to do with the wavelength and frequency of our standing wave. It only has to do with the actual spring coils, their density, their tightness, something beyond the curriculum. But just know that the speed of the wave is fixed side to side, unless you change something like tighten the spring or do something, lessen its density. So then, when you know the wavelength, twice the length of the spring, you plug that in over here, and you will get the frequency of oscillation. That in the first harmonic is called the fundamental frequency. It's just a name we call it. First harmonic vibrates in the fundamental frequency. As you saw in the video, if you shake your hand at this end faster, so we do slow and then we go a little faster, then what happens is we get another segment. The spring will vibrate in what we call the second harmonic. And if I were to snap a photo of that at that instant, then I might see something like this. Or if I snap it later, maybe I see a trough and then a crest. Or at another time I snap it and it's all horizontal because that's the wave oscillating. But at this moment it looks like this. So we see 3 nodes this time. At the ends there's 1 node, and there's 1 in the middle because these points go like this. But the middle, if you go back, look at the video, there are points that never move or hardly move. And now we have 2 antinodes, places of maximum motion. So just a note, there are 3 nodes and 2 antinodes. And we'll see that pattern. The number of antinodes is always equal to the harmonic number, but there's always an extra node because there's 1 extra at the end. There's always node, antinode, and then an extra node at the end. All right, now if you look, instead of the wavelength being twice the length of the spring, what we see here is we see that the spring actually contains 1 full wave. So whatever that wavelength is, like I said, maybe it's like 9 meters long, then the wavelength is 9 meters because it's just the length of the spring. So we put this in the fixed velocity, which stays the same no matter how quickly I wiggle this end. The speed this way stays the same. I plug in the new wavelength, which is half what it was before. Over here it's 2L, over here it's L. So if we have half the wavelength, we have to go at double the frequency. So the first harmonic like this, and then the second harmonic is faster. And then I create that standing wave. If I shake faster, then I can establish the third harmonic, snap a picture, and it might look something like this. 2 crests and 1 trough. Or snap it at another time, I might have 2 troughs and 1 crest over here. And so that's the third harmonic. I have all the nodes labeled. There are 4 of them. 1, 2, 3, 4. 4 nodes. And 3 antinodes. 1, 2, 3 antinodes. And the amplitude, again, I think I forgot to mention it before. It's always from the equilibrium position to the peak or to the trough. It's not the whole distance that antinode moves. In other words, if this is 1 meter, then this point actually moves 2 meters down, 2 meters up, 2 meters down, 2 meters, but the amplitude's 1 meter. Okay, now how do I find the wavelength? To find the wavelength, what I need to do is first find the length of one of these segments right here. Okay, so I do that by dividing the length of the spring by 3. 1, 2, 3 segments of equal length. So this is 1/3 of the length of the spring. But that's not one wave. One wave is not a crest. It's a crest and a trough. So I take that 1/3 length and I double it times 2, and I have the wavelength. So again, if this is 9 meters, then this is 3 meters, and the wavelength is 3 and 3, or 6 meters. So I plug that into V equals lambda times frequency. This is the same. The wavelength is now a third of the fundamental frequencies, or the first harmonic. So in order for this product to remain the same speed, I need triple the frequency. So the fundamental frequency, first harmonic, I'm shaking slow. The second harmonic, I'm shaking faster. The third harmonic, faster still, triple the frequency of the original. Fourth harmonic, faster. And as you saw in the video, you have to shake faster and faster to create higher harmonics. Well, we could go on, but no need to. I just want to point out that there is a pattern here. And so we saw that in the first harmonic, the wavelength was twice the length of the spring. You could go back and look at your notes. Second harmonic, it was just the length of the spring. And then in the third harmonic, it was the length divided by 3 times 2. If we take this middle one and we multiply by 2 over 2, we see a pattern. 2L is always in the top. And then the antinode number is in the bottom. 2L divided by 1, 2L divided by 2, 2L divided by 3. In other words, the formula, if you wanted to remember it, is twice the length of the spring divided by the number of antinodes. This is not on the reference table. And the reason why, I think, is because they just expect you to be able to look at this and reason out how to calculate the wavelength. Okay, find the length of one segment by dividing by how many antinodes you have. And then, so that's L over 3. And then double that to get a full wave. And if you do that pattern by just looking at the picture, you will essentially be doing this formula all the time. Okay, but if you want to memorize the formula, you're welcome to this. Nothing against memorizing, but okay, here's just a little simple example. So I've got a 0.64 meter guitar string, and it's made to vibrate in the 5th harmonic. So that, by the way, I looked up, is about the length of an acoustic guitar string, 0.64 meters, so it's a certain length. And you make it vibrate in the 5th harmonic. If you know someone who plays guitar, they know how to make harmonics. You could ask them, and there's kind of a nice sound, okay? And the waves travel at 17.8 meters per second on the string. Again, that is only changed when you tighten the frets to tune the guitar. Once the guitar is tuned and it has a certain steel thickness and toughness and a certain tension, this stays the same no matter what frequency you make the string vibrate at. So then part A says sketch the wave in the 5th harmonic, right? And then label the nodes and antinodes, determine the wavelength, and then determine the frequency of the wave. So here's a little picture. I draw crest, trough, crest, trough, crest. So notice 1, 2, 3, 4, 5. That's the 5th harmonic. I have 5 antinodes. And by the way, 6 nodes. Okay, so that's always the case. The number of antinodes is equal to the harmonic number. The number of nodes is an extra one. Okay, so I didn't use the formula here. What I did is I took the length of the string and I divided by 5 to get one segment right there. And then to get one wavelength, I double that, so I get a crest and a trough. Okay, and so that's 0.256 meters. Then I simply plug into V equals lambda times frequency, the V that was given, the wavelength I just determined, and I get the frequency of the 5th harmonic on that guitar string. So that is the topic for today, standing waves. Again, you need to know how they're made. Okay, so you can either have 2 people sending waves opposite direction, then they interfere, they will make an illusion of a standing wave. Or you could have one person sending a wave on a spring toward a wall where the spring is fixed. And then you have to be able to analyze the first harmonic, know that lambda is twice the length of the spring, use this formula V equals lambda times frequency to get the frequency. Second harmonic, do the same analysis, realizing that lambda is the length of the spring. Third harmonic, right, analyze that. And there's an example. So that's standing waves. See you in the next lesson.